So yeah, I will be talking about this quantum security of the Bitcoin backbone protocol and the quantum multi-solution Bernoulli search. This is a joint work with Juan, Garay, Aggelos, Kiayias, Fang, and Petros, Wallden. So firstly, to present some motivation, as we all know, Bitcoin is the first and most popular decentralized cryptocurrency. It can build a public distributed ledger. And the Bitcoin backbone protocol that was also mentioned in the previous talks is an abstraction that captures the essential features to formally treat the security of the Bitcoin. And at the basis of the security lies the concept of proof of work, in which essentially parties are proving that they're spending some computational resources. But now in the quantum landscape, we know that quantum computers can promise, in some cases, significant computational advantages. And in this work, we propose to study how the security of the backbone protocol would change in the setting in which adversaries would possess quantum computers. So firstly, I would like to give some very quick quantum background. So as we have in the classical computers bit strings, in the quantum keys, we would have qubit strings, which can be thought as vectors. And then a general quantum state is basically just a unit vector, which is composed of qubit strings having complex coefficients. So such an example is the state psi, which is a superposition between the state 0, 1 with coefficient 1 over square root of 2, and the state 1, 0 with coefficient I over square root of 2. And one way to manipulate quantum states is through gates, which are essentially linear maps. And such an example is the Hadamard gate, which essentially maps 0 to an equal superposition between the 0 state and the 1 state. Another important concept in quantum computing refers to quantum measurements, which are probabilistic in nature. So if we have a state phi, which is the superposition sum over x, ax, and the state x, then the measurement would result in obtaining some outcome x with probability ax squared. Another important quantum notion particular to our work refers to how we are able to access a classical function in a quantum way. So we know that if we have a classical function f, then there always exists a quantum circuit UF, a unitary, which has the following effect. So if we query it with the input state xy, so in the first register x and in the second register y, then UF would map this input to the quantum state x, and in the second register y XOR f of x. And now if we are to use the linearity of the operation UF, then we can actually use superposition queries, and this would lead to obtaining a superposition over AXX in the first register and f of x in the second register. Now, since we mentioned the possible quantum speedups, and since we also want to say something that is relevant to our problem, we can mention the searching. So in a search problem, we have an n-element database, and we know that to find the solution, classically, we just need n queries. But quantumly, using Grover, we know that we only need square root of n, which is also the optimal algorithm. And now I just want to give a very brief introduction to the Bitcoin backbone protocol of Garay et al. So the blockchain is essentially formed of blocks containing transactions. And the backbone protocol is ensuring that parties are maintaining the blockchain in a distributed fashion. Then to generate a new block, parties need to solve a proof of work. And finally, we know that each party has a local chain. And essentially, they are trying to update with the longest chain and then extending it. And regarding the security model, we have n parties. All parties are either honest or adversarial, have classical computers. And we have T adversaries and n minus T honest parties. And between these two numbers, there exists an honest majority assumptions, which is required to ensure the security of the backbone protocol. And then in a single round, in order to break a proof of work, each party, either honest party or adversary, has Q queries to the function age, where age is essentially modeled as a classical random oracle. Now, in the post-quantum security of the backbone protocol, we model the adversary. First of all, we know that if the adversary is quantum, the most powerful tool he can use is essentially querying H in a superposition. So for instance, as we have seen in the quantum background part, you can perform queries of the type y1 plus yn, and this would be mapped to y1 h of y1 plus yn h of yn. And in our case, we consider that the adversary is a single quantum adversary having capital Q queries, which represent the joint computational effort of all the parties under his control. So a proof of work is essentially just a mean for a party to convince that he has invested some effort for solving a task. And this task is particularly finding a witness Y such that age applied to X and Y is less than D, where X represents the hash of the previous block. And D is some parameter known as the difficulty level of the proof of work. And then once a party is successful in producing the proof of work, he can add a new block to the blockchain. And now when we talk about the security of the backbone, we mostly refer to the two basic properties, to the common prefix and the chain quality. So the common prefix essentially means that the blockchains held by the honest parties may be different, but they must have a large common prefix. And the chain quality essentially tells that the number of blocks which are created by an adversary in an honest party's blockchain must be bounded. And then in the classical backbone, to show these properties, the analysis was based on obtaining bounds on the number of proof of works broken by the honest players and adversaries within a set of rounds. And lower and upper bounds on these values were mostly derived from the honest majority assumption. So our main results can be summarized as follows. We essentially show that the protocol security, namely that the two properties hold in the post-quantum setting, under the assumption that the quantum adversary is bounded in a suitable way in the quantum random oracle. So what do we mean by a suitably bounded quantum adversary? We essentially mean that as long as we can bound the quantum adversarial hashing power relative to the honest classical hashing power, then the security of the protocol holds. And more specifically, we show that the security holds as long as the quantum queries of the adversaries are such that each of them is worth p to the minus 1/2 of the classical ones, where p represents the probability of success of a single classical query. And another consequence of this is that the wait time for safe settlement, so essentially the number of rounds you need to wait until you have the same level of security as in the classical setting, it actually matches up to a constant the safe settlement time against classical adversaries, which is quite surprising. So let's see what is the underlying abstract problem that the adversary is trying to solve. So essentially, the quantum adversary is trying to produce a chain which is longer than the honest chain. And to analyze this, we need to bound what is the maximum length of the chain that he can produce. So abstractly, this would translate to a search problem where the output represents a chain of hashes. So essentially, the output of one hash is fed as the input to the next hash. And to be more precisely, the problem chain of posts can be described as follows. So we are given n quantum queries and the starting point x0, as well as n random functions h0 up to hn-1, where each of these functions are independently sampled. Then the task is to find a sequence of length k, y0 up to yk-1, such that the following recurrent relation is respected. So such that xi plus 1 is equal to hi applied to xi and yi. And also xi plus 1 must be less than this parameter d. So essentially, we can see that directly solving the chain of posts for a quantum adversary is a very complex task. So first of all, we cannot a priori break it into separate search problems. And also, we can also imagine that the quantum adversaries would be able to perform a very complex search type of algorithm to output directly a chain of proof of works. So our approach is to actually use a series of reduction to bound the maximum length achievable for the chain of posts problem. So now to quickly present the proof roadmap we use. So to analyze the query complexity of the chain of posts, we firstly define a simplified problem, which is called Kiayias search. Then we find the relation between the query complexity of the chain of posts and the Kiayias search problem. And then we focus on analyzing the quantum query complexity of this latter problem. And to do this, we need to derive a threshold direct product theorem for this type of randomized search problems. but I'm going to go into more details about how we are achieving this. And finally, once we established the query complexity of the chain of post problem, then we can complete the post-quantum security of the Bitcoin backbone by essentially giving tight characterization of the probabilities of the protocol's properties. And essentially, this also allows us to derive a post-quantum honest majority condition, which, as we have seen, essentially represents a relation between the quantum computational hashing power and the classical hashing power of the honest players, and also the required number of rounds for safe settlement in the case of quantum adversaries. So let's see what is the relaxed problem. So the relaxed problem, called K-bear search, is essentially asking for the maximum cardinality of independent proof of works given n quantum queries. More specifically, the K-bear search can be described as follows. So we are given a function f that has single bit outputs, which is generated by the following Bernoulli sampling procedure. So essentially, for each input x, we are going to independently set f of x is equal to 1 with some probability p, which p is some parameter, and with equal to 0 probability 1 minus p. And the task is to find key preimages of 1. So to find x1 up to xk, such that f of xi is equal to 1. And we can see that as compared to the chain of post problem, now we no longer have the requirement for the blocks being sequential. So we just have a sequence of k blocks which can be independent. And now our goal is to find the relation between the query complexity of the chain of post and the K-bear search. And specifically, we show that for any adversary having n quantum query, it can produce a chain of length k with probability p1 of nk. And then if for any quantum adversaries a prime having n quantum queries, he can solve the K-bear search problem with probability p2 of nk, then the following relation must hold between the two probabilities. So specifically, the probability of solving the chain of post with n quantum queries is less than the probability of solving the K-bear search with n plus k quantum queries. So now it essentially suffices to just study the query complexity of the simplified problem of the K-bear search. And the main question we are asking is, if an adversary has n quantum queries, what is his maximum probability to solve K-bear search? So to find those key preimages. And to do this, we derive a threshold direct product theorem. Technically, this relies on using the recording technique for quantum queries in the quantum random oracle developed by Zandri, but which was developed for uniform distributions. So for functions sampled according to, for functions sampled uniformly. Whereas if we recall, in our case, we had a function sampled from a Bernoulli distribution. So one of our main contributions is to modify this recording technique framework to allow for functions sampled non-uniformly. And this new framework can be of independent interest. And essentially, the main result regarding the query complexity of the K-bear search problem can be summarized as follows. So if a quantum adversary A has n quantum queries, then the maximum probability that A solve K-bear search to find key preimages is essentially E times n times square root of P over K, everything to the power of 2K, where P refers to the probability of a successful proof of work using just a single classical query. And now I want to describe how the recording oracle technique works and how it allows to tell something about the query complexity of this problem. So essentially, this framework developed by Zandri allows to keep track of the quantum adversary's knowledge when interacting with a uniform random oracle. So specifically, if you suppose a uniform sample functions f, then as we have seen in the quantum background part, we can query f in a we can query f quantumly by performing queries of the type xy, which are going to be mapped to xy with an extra phase of -1 to the power of y times f of x. And the key observation in the recording technique framework is that a quantum adversary cannot distinguish between the following two settings. So in the first setting, we have the function f being sampled uniformly at random. And in the second setting, we are essentially adding an extra register, which is going to represent the uniform superposition of all possible functions f. And when I say here get f, I actually mean the table of truth of the function f, which, and very importantly, this extra oracle register is not accessible by the adversary. And to make it a bit more clear, so suppose that an adversary is going to perform a general quantum query. So it's going to be a query of the form sum over xi, axy, state xy. And then the state after the system, after we perform the query, is going to be the same in the input register. And then we can see that actually this phase that we had before, so this -1 to the y times f of x, can actually be moved to the second register. So it can actually appear right here. And this very important observation tells us that a query of the adversary is actually modifying the oracle state. And we are going to actually use the oracle state to learn information about the adversary's knowledge. And as you mentioned before, very importantly, he cannot access this register. So now, to make the presentation a bit easier, I'm going to introduce some notation. So we are going to consider the string p of xy, which is essentially the all zero string, except that on position x, we have value y. By using this notation, this essentially means that y times f of x is the same as considering the inner product between the string p of xy and the table of truth of the function f. And then we are just going to use the state we obtained, the state of the system after the query, and we just replace the y times f of x with this new expression over here. Well, we can denote this as the primal domain. So this is the state after the adversary performed the query. But now comes the nice observation. So essentially, if we are going to apply Hadamard gates on this second register over here, so on this superposition over all possible functions, this whole state is going to become just the state consisting of the classical string p of xy. So this essentially represents a quantum state having 0 everywhere, except that on position x, we have value y. And we are going to denote this as the dual domain, also known as the Fourier domain, because essentially we apply the Fourier transformation. And then we can also generalize this and say that after t queries of the adversary, the oracle state, so that, that this extra register is just going to become the XOR of t strings of the form p of xy. And this nice observation allows us to keep track of the evolution of the adversary's query in the Fourier domain. So essentially, to do so, we just need to start with the all zero state. And then after each adversarial query, we are just going to XOR to d a value p of xy. So this observation tells us that after t queries of the adversary, the oracle state will have at most t positions equal to 1, because essentially we are just XORing each time with p of xy, which has at most one non-zero position. And this essentially tells us that any event about the adversary's knowledge of the function f, of the underlying random oracle function f, can be translating into investigating some corresponding property of the oracle register, so of this state d. And this is how we actually keep track of the adversary's knowledge about the function f. So in our case, we have to modify this recording technique to accommodate for the K-bear search problem. And essentially, we now allow for function sample according to Bernoulli distributions. So as you have seen previously, in the uniform case, each query would had the effect of modifying exactly one position, either from 0 to 1 or from 1 to 0, of the oracle state in the Fourier domain, so in the dual domain. But now in our case, because we have a function sample according to this Bernoulli distribution, the initial oracle state would be a Bernoulli superposition over all possible functions. Hence, we cannot use this view between the primal and the Fourier domain as before to record the queries of the adversary. Instead, our approach is to consider a different dual domain, and then to extend the primal dual domain to accommodate for Bernoulli distributions. Switching between the primal and the dual domain is no longer going to be achieved through this Fourier transformation, so by applying Hadamard gates, but by using a different unitary UP, which has the parameter P over here, and which essentially is mapping the all zero state to the Bernoulli superposition over all possible functions. And intuitively, you can think of UP as just rotating the zero states toward one state using this parameter P. So now with this observation, we can also keep track of the evolution of the oracle state in the dual domain as we had in the uniform case. So as before, we will again start with the oracle state being initialized in the all zero state. With the main difference is that while before we had switching between 0 and 1 with each quantum query, now we will essentially rotate one of its qubits using this unitary UP. And this means that after T quantum queries, we will essentially have at most T rotated qubits in the oracle register. And the rest of the qubits should remain 0. And essentially by keeping track in this way of the queries of the adversary, then by just examining how many non-zero entries are in the oracle register, we can tell information about the adversary's knowledge. And finally, in order to say something about the success probability of the adversary, we need to return to the primal domain. And to do this, we essentially need to apply back the unitary UP to the oracle register. But the trick here is that you can see that now if I apply UP to a 0 position, and then I apply a measurement, because of the probabilistic nature of measurements, this means that even a query that has never been, even a position that has never been queried before can collapse to a measurement outcome 1. But it's not an issue because this is essentially just capturing the adversary strategy where he's just outputting some candidate preimages which are just random guesses. So essentially, he didn't make any queries to determine these preimages, but he's just making some random guesses for some of the preimages. So essentially, this tells us that analyzing if the adversary was able to solve the K-Bear search just corresponds to examining if there are at least K non-zero entries in the oracle register. And then to bound the probability of this latter event, we just need to examine after each query how close we are to the desired oracle state, the one having at least K non-zero entries. So now, now that we have established the query complexity of the K-Bear search problem, so now that we have seen what is the maximum probability of the adversary to solve the K-Bear search problem, we just need to combine this result with our relation between the query complexity of the two problems, and then we can derive our main result about the complexity of the chain of pose. Specifically, we know that any quantum adversaries having n quantum queries can obtain a chain of pose of length at most k with this probability over here, where we recall that the p appearing here refers to the probability of a successful proof of work using a single classical query. So now that we have established what is the hardness of the chain of pose problem, we are going to use it to identify the conditions under which the common prefix and the chain parity property can be obtained in the presence of quantum adversaries. And to do so, we are going to proceed similar to the classical analysis. So first of all, we are going to define a notion of post-quantum typical execution, defined in the presence of honest players and quantum adversary. Then we are going to prove that under post-quantum typical execution, the desired properties follow for suitably chosen parameters. Finally, we are going to determine a post-quantum honest majority condition under which a typical execution occurs with high probability. So essentially, this allows us to obtain the following table of results. So essentially, we can tell what is the post-quantum honest majority, which, as we have mentioned before, it represents a condition on the number of quantum queries of the adversary. That specifically, it must be less or equal than f times 1 minus f over square root of p, where f represents the probability that at least one honest party finds a proof of work in a round. And along with that, we can also determine what is the maximum expectation, what is the maximum expectation of adversarial number of proof of works that he obtains during S rounds, and then also the probability of a typical execution. And finally, from the probability of typical execution, we can also determine what is the number of rounds required to reach the same level of security as in the classical setting. And here is where you observe that in the quantum case, it matches up to a constant the number of rounds in the classical setting. And I think I'll stop here.